right. Oh, before we get started, just a quick reminder. So we're going to have an exam on chapters 5 and 6 next Thursday. Oh, and I was planning to do this before I came to class, and then something came up. I have last year's exam. There's just one thing I'm going to tweak, because last year, for some reason, we included 7.1, which I'm not going to do this time. So I'll just have to find whatever problem on last year's exam was about 7.1, and I'll take that one off. All right, and then I'll post what's left. Oh, and then the other thing I wanted to show you. Probably shouldn't have turned on the video yet, but we can edit this part out. So all the homework assignments are on Blackboard now. I did tweak 6.1 a little bit, not too much. There were only 2 problems that had a whole bunch of parts to them. Okay, so there they are. This is what I'll be looking for Thursday next week. So I still have the Chapter 5 homework, which I'm going to try to return to you on Tuesday. And then, so the other thing that will be happening Tuesday, we'll review everything you want to review. And also, that's, I guess, the day you're going to, Professor Kanemoto is going to go over your last Maple homework. Was it Maple? Yeah. Okay. So Thursday's kind of an all-around review day. All right. So, yeah, I noticed that for 6.3, I didn't have to change this. It was already like that. I think I kind of sort of remember why I did that last year. Okay, so back to finishing up 6.3. 7 women and 9 men are on the faculty in the math department at a school. I wonder how close that is to Merced College. I think we have more women than that. How many ways are there to select a committee of 5 members of the department if at least 1 woman must be on the committee? So this hasn't come up very much, but whenever I do any kind of counting or probability, I always talk about how be on the lookout for the words "at least." Because usually when you see "at least," it means it's going to be easier to count indirectly. Okay? So if you don't have at least 1 woman, so where are we, number 6A. If you don't have at least 1 woman, then you have no women, right? So the way we're going to do this is we're going to count the total number of committees and subtract the number that don't have any women. And I think I like this pen better. All right. So hopefully somebody can tell me, what is the total number of ways to pick 5 people to be on this committee? How do you do that? This is what we talked about last time. I'll give you a great big hint. What choose what? 16 choose 5. That's right. If we're not paying any attention to men, women, whatever, we just want 5 warm bodies, then the number of ways to pick those 5 warm bodies is 16 choose 5. Right? Okay, now, I'm going to include an extra step in this counting the number that don't have any women, because this will be helpful. Maybe next time you're going to have to count how many committees have exactly 1 woman. Exactly 1. All right? So when all of a sudden you're paying attention to how many men and how many women are there, you can think of that using the product rule. So the first thing I'm going to do is pick the men, and then the second thing I'm going to do is pick the women. I know in this case I'm not picking any, but maybe next time I will. All right, so how many men am I going to have on the committee if I'm not going to have any women? I'm going to have 5. How many do I have to pick from? I don't have 16. I have 9, right? So that's how many ways there are to pick my 5 men. And now I'm going to pick some number of women, and that number may be 0. And in this case it is, right? I have 7 women to pick from, and it just so happens this time I'm not going to pick any of them. Okay? So it's a product rule. First pick the men, then pick the women. Okay? And I am going to... I am not going to. Okay. Left my calculator laying around somewhere. So I'm going to need somebody to help me. What does 16 choose 5 come out to? And I told you could do that on the calculator. You don't have to use the formula. I'll start doing it by hand, and you can stop me if you... Okay, so let's see, what can we do here? We could do 4 times something. 4 times 3 can wipe out 12. And 2 goes into 16, 8. 5 goes into 15, 3. What does that come out to? 4,368, did you say? 68. Okay, so that's the total number of committees, and then the ones that are just men. Well, I can tell you 7 choose 0 is 1, so we don't have to worry too much about that part. 9 choose 5. That one I might be able to do. 5, 4, 3, 2, 1. Goodbye 5, goodbye 6. 126. Okay, for a total of, so there's 4,368 committees total. There are 126 that are just guys, and that means that the number that have at least one woman on them is 4,244. 42, thank you. 42, 42. Right? Make sense? Okay, let's see what else. Okay, interesting. This is my life a little bit right here. So I think I mentioned to you guys once that I'm the faculty union guy on campus. And one of my jobs as the faculty union guy is that whenever they put together a hiring committee for, for any job on campus, usually the faculty union has to nominate one person to be on the hiring committee. And I hear a lot of flack from human resources that these hiring committees are not diverse enough. All right, so this looks like the kind of thing I might be thinking about. They would definitely want at least one woman and at least one man on the committee. They don't like committees that are all men or all women. All right. So it's kind of similar to what we just did, except maybe just a little bit more complicated. Couple of different ways you could do that. I think maybe the easiest way would be take the total number, which we already have, subtract the number that are all men, which we already have, and what else? Is there anything else I want to get out of there? I don't want any committees that are all women. So I need to subtract the number that have no men. Right? Okay. You guys should think about what is this number, because I think you can do that. That's the one thing we don't already have. I'm going to do the easy part and just copy down the stuff we do already have. All right, think about that for about half a minute. I don't think this is going to come out to be a very big number. What does that come out to? This number here. 7 choose 5 times, I'm going to throw in the 9 choose 0, even though it doesn't really do anything. Throwing that in there, I think, will be helpful if the next question is, how many committees have exactly 3 men and 2 women, let's say, because you do it exactly the same way. 7 choose 5, I want to say that comes out to 21. Is that right? So there's only 21 committees that don't have any men on them. All right? Okay, so instead of 42-42, I think it's going to be 42-21. Right?
So basically you're eliminating the cases where there's no men and no women.
Correct. Yeah. Now, I'm just trying to think. Sometimes you have to worry a little bit about when you do a problem like this and you're saying, okay, let's get rid of one category of things that don't fit that description, and then let's get rid of another category of things that don't fit that description. Sometimes you have to worry a little bit about, could I be throwing out anything twice? In other words, is there any overlap between these two groups? And the answer this time, I think, is pretty clearly no. There's no overlap, right? The committees that are all men and the committees that are all women, all right, none of those are the same committee, all right? I'm having trouble thinking right off the top of my head of an example where that could happen. Anyway, just be on the lookout for that, all right? This time it's fine, okay? All right, so I think there's only one more example. Okay. I think you guys can probably handle this one because it's very similar. How many ways are there to select 12 countries in the United Nations to serve on a council if 3 are selected from a block of 45, 4 are selected from a block of 57, and the others are selected from the remaining 69? And I think this is going to be one of those problems where, and we had one like this the other day, the answer came out so big that we didn't even bother to try to do it out. Remember this one? Came out to a great big number, and so we just left it in terms of P of something something, and I think there was a factorial in there. Okay. Well, definitely if it's a big number, leave it that way. If it comes out to something like this, I would rather you just do it out. All right. But no, that's probably okay. Definitely if it's a great big number, it's okay. While you're doing that, okay, so select 12 countries, including 3 from 45. I'm writing this down because I'm about to, I need to put up your notes from 7.1. 4 from a block of 57, and the rest from the remaining 69. Okay. All right. So while you're doing that, let me really quick put something on your blackboard. La-da-dee, da-da-da-da-da. Okay, there it is. All right, so you see it's really similar to what we were just doing. First pick the 3 countries. How many ways to do that? Go ahead. How many ways are there to pick the 3? 45, choose 3. So this is just like picking the men and the women. And then any selection of those 3 countries can go with any selection of the 4 from there. So that would be like that. Okay. And then how many more do we have to pick? $69, choose what? 5, right? Because you have to pick a total of 12. Okay. And that, I think, we'll just leave like that because that's a great big number. Oh, my goodness. Forget about it. All right. Is that good? That is a lot. It's a lot of combinations of countries. Well, it's a lot of countries, too. Even more combinations of countries. All right. So, draw a line right there. That's the end of what's on exam 2. All right. So, this time we're going to try keeping all the probability stuff together. That'll go on the last exam. Yes. Review on Tuesday. Okay. This doesn't have any animations in it. I'm sorry. Everything's all going to come up at once. Didn't get a chance to do that. I'm not too worried about, the temptation when you're hearing about something new that's not going to be on the next exam is la 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 la, not listening. I'll think about this later. There's still a lot of counting in this, so you don't have to worry about this messing you up, all right? Especially this first section. I think that's why last year I felt okay about including this section, but I'm not going to do it this time. Okay, so when we talk about experiments in probability, we're not talking about dissecting frogs. We're just talking about doing any kind of procedure that has different outcomes. Rolling dice, flipping coins, those are the tired old cliche probability situations. All right, so an experiment is any procedure that gives you a set of possible outcomes. The sample space is the set of possible outcomes. So if you're rolling a die, one die, the sample space would just be the numbers 1 through 6. And then an event is any subset of the sample space. Like in a lot of board games, something special happens if you roll doubles. So an event could be you roll doubles, and so you look at what outcomes fit that event. It would be like 1-1, 2-2, 3-3. Okay? All right, so now, definition of probability of an event with finitely many possible outcomes. If S is a finite, non-empty sample space, all right, so it has a finite number of outcomes that are equally likely, that's really important. What makes a lot of probability questions hard is that the outcomes are not equally likely. So I think we might be looking at some not equally likely stuff later. Yeah. Okay. All right, and E is an event. Then the probability of E is defined to be how many outcomes are in the event over how many outcomes are in the sample space. Okay? So, well, let's see. I probably have an example here. Oh, okay. Example coming up. So the first thing I wanted to do, I learned pretty early on in my career, the first time I taught probability, that not everybody's familiar with what a deck of cards looks like. Not everybody plays cards. So lots of playing card examples in probability. So here is your standard deck of cards. It has 52 cards. They come in 4 different suits, which are called clubs, spades, hearts, and diamonds. And then within each suit you have 13 different kinds of cards. They're called kinds. They're called denominations. You have the ace, you have the numbers 2 through 10, and then you have the face cards, Jack, Queen, King. Okay? All right, so with that in mind, all the questions come up at once. Didn't animate it. What is the probability? Oh, okay. Oh, all right. First question isn't about cards. What is the probability that a randomly selected day of a leap year is in April? Most of the time we pretend it's not leap year when we do probability, just because it's a pain to take that into account. So, all right, so the probability of, let's say, April. How many days are in April? Do you know? 30. How many days are in a leap year? 366. Okay. All right, and I'm not going to be picky about simplifying fractions. You can write these as decimals. All right. I mean, it's always nice to simplify the fraction. A fraction like that, I would probably just write it as a decimal. It's a little bit easier to understand. Okay? But we'll just leave it like that. Okay? So this is how many outcomes are in your event. This is how many outcomes are in your sample space. 30 days in April divided by a total of 366 days in the year. Okay. What is the probability that a 5-card poker hand contains exactly 1 ace? All right. Well, if we could back this up, you know what I kind of wish I had done is in the last section said how many different poker hands contain exactly 1 ace. And then we would have already done a lot of the work. All right, well, let's do it this way because we know we need how many outcomes are in our event. We know we need how many are in our sample space. So let's start with the sample space. The sample space is the number of different poker hands. All right. So how many ways are there to pick your 5 cards out of the deck? Does the order that you hold the cards matter? No. No, it doesn't. Okay, so that's going to make it a combination. So what choose what? Total number of hands. 5 cards. 52 choose 5. Okay. If somebody could tell me what that comes out to, I think I remember it's like 2,500,000 something. 2,500,000. Can I guess what it is? I think I remember what it is. Is it this? I've done it so many times. I didn't do it in my head. I had it memorized. All right. Okay. So there's that many different poker hands. So now we have to count the number that have at least one ace. And I think that's something you can do because it's just like something we already did today. Number with at least one ace. So this is just like picking your committee. All right. That had at least one woman, I guess it was. Bring this picture back up. So hopefully you realize the easiest way to count that is to count the number that don't have any aces and subtract that from the total, right? Okay, so the total is 52, choose 5. Okay. So then how many hands have no aces? First you have to pick your other 5 cards. How many do you have to pick from? How many? 48. There are 48 cards that are not aces. And then this part's optional, but again, it'll be helpful later. Pick the aces. In this case, you're not picking any. Okay. What does 48 choose 5 come out to? Because that I don't have memorized. Hmm? $712,304.
1,000,000.
Oh, 1,000,000. Okay. Okay. So it actually turns out that most poker hands don't contain any aces. That's not too surprising. And then what does that come out to when you subtract? 886,656. Okay. So the probability of having at least one ace is, and I definitely would not leave the answer like this, not with these big numbers, 886,656 over 2,598,960. That's somewhere in the ballpark of what, about point and 3 something. 0.34? Good enough for me. Okay, so if you play poker, you have about a 34% chance of getting an ace. All right? It's just counting. You're basically doing 2 counting problems and putting the answers in a fraction. That's all. Oh, no. Okay. So you know what we're going to do? We're going to call that problem number 1.5. What is the probability? I read it wrong. It was supposed to be exactly, and we did at least. No, it's not that simple, unfortunately. I'm going to tell you what the answer to 1 over 52 is. You could make a question that sounds kind of similar. Okay, so we just did a different problem. The hand contains at least one ace. That's the great thing about being the instructor. You get to change the question. Okay. Okay. Well, you're getting extra instruction right now. We're still going to do number 2. We'll do it right now. What's the probability that the hand contains exactly one ace? Okay, let's do it. This is exactly why I kept including the 4 choose 0 or the 9 choose 0, because now we're actually going to need that. Okay? So this time the event is contains exactly one ace. Okay. Actually, I shouldn't have. This should be like this. Okay. So first we're going to pick the cards that are not aces. Pick non-aces. All right. And if I have exactly one ace, how many non-aces do I need? I need 4. So there are 48 choose 4 ways to pick the non-aces. And then I have to pick the ace. How many ways are there to pick the ace? There are 4. Or you can say 4 choose 1. I'm going to write 4 choose 1. 4 choose 1 is 4. Okay, so that was an easy fix. What does that come out to? Hate not having my calculator. Thank you. Oh, that's interesting. There you go. When did I ever say they weren't good for anything? All right. What's interesting is that that's, well, it's a little bit less than the number that have at least one ace. At least one ace. Well, of course it's going to be less than that. All right. Because that number includes this number. Okay, so the probability of exactly one ace is 778 or 320 over 2,598,960, and that comes out to be about 0.29, did you say? All right, so about a 29% chance of getting exactly one ace. All right. Okay. Make sense? Now we get to number 3, and I think number 3 is just a little bit crazier. Different numbers. Yeah. Kinds means numbers. They can be the same. Well, you would have to have a couple that are the same suit. Oh! If you have 5 cards, you must have at least 2 cards that are the same suit. That's an example of using what? The pigeonhole principle. I just thought of that. Yeah, 5 different cards. So whenever I do these poker problems, what I like to do, I think it's helpful, is I'll actually write an example of what's a hand that looks like that. So 5 different kinds would be something like a 3, an 8, a 10, a jack, and a king. And I don't really care what the suits are. Let's say the suits are hearts, hearts, diamonds, diamonds, and hearts. I'm picking on diamonds and hearts because they're easiest to draw. That's the only reason. All right? Okay, so that's an example. All right, so now we're going to get into slightly crazier counting. All right? So it is a probability, which means the number of outcomes in the sample space is still 2,598,960. At least that part's done. Okay. So here's how I'm going to count the number of outcomes in this event. The first thing I'm going to do is count how many ways are there to get 5 different kinds. So first choose your 5 different kinds. How many different kinds are there? Not paying any attention to suits? There are 13, right? So the number of ways you can pick your 5 different kinds is 13, choose 5. Okay. So at this stage, you have identified what kinds of cards you have. You still don't know what suits they are, though. All right, so at this point, you know that you have, for example, 3, 8, 10, Jack, King. Okay. But your hand is not completely specified until you also say what the suits are. So even though I don't care what the suits are, I still have to count them, all right? Because there are, well, quite a few different hands in the 2.6 million. There are quite a few different hands that have those same 5 kinds in them. So, so the second question is, what suits are the cards? And this is not going to be a combination, and it's not going to be a permutation either. It's actually going to be something simpler than that. How many choices are there for the suit on this card? How many choices for the suit on that card? How many choices for the suit on that card? 4, 4, 4, 4, 4. So the number of ways to assign the suits is 4 to the power 5. 4 times 4 times 4 times 4 times 4. Okay. All right, so the number of different hands that have 5 different kinds of cards in them is 13, choose 5. 13, choose 5, so it should be some kind of manageable number. One 43, 12, 87. But then we have to multiply it by 4 to the 5th. That's going to be a pretty big number. 1287 times, I think it's 1024, comes out to 1 million what? If you guys have your calculators with you, you should have them out so that you're, getting the practice actually using the combination permutation. Go ahead. What is it?
1317 888.
All right. Interesting. So the probability of getting 5 different kinds is about 1.3 million over about 2.6 million. It's just about 50-50. I think it's a tiny bit more than 50-50. What is it, 0.5? Oh, 50.7? Okay, so we'll call that about 0.51. $1,317,888 over 2,598,960. So I don't know if any of you actually play poker. I have played. I don't play very much. I've played just enough to know what the different good hands are in poker, or the hands that are worth anything. A hand that has 5 different cards in it is usually not worth anything unless they're all the same suit, which makes it a flush, or it's a straight, like 2, 3, 4, 5, 6, right? Those are worth something, otherwise not worth anything. Oh, yes. All right. Let's see. Why don't we do one more? One more, and then we'll take a break. What's the probability that a 5-card poker hand contains a 3 of a kind and then 2 cards of 2 other kinds? And that kind of hand in poker is called a 3 of a kind. It's not worth very much. I think it is the second lowest hand that's worth something, I think. So there's 1 pair, and then I think next from the bottom is 3 of a kind. I think 2 pair is better than 3 of a kind. Or is it the other way around? Oh, it is. Okay. So it's the third worst hand that's worth something. Okay. Anyway. All right. So kind of similar to what we just did. So first I'm going to write up my example. So 3 cards of one kind and 2 cards of 2 other kinds. Let's say 8, 8, 8, 9, queen would be an example of a hand like that. Doesn't matter what suit this is. Doesn't matter what suit this is. Now that some of the cards are the same kind, they're going to have to be 3 different suits, right? So one of them's a heart, one of them's a diamond, and darn it, I have to draw something else now. I'll draw a club. Okay. So I'm going to count how many different hands are like this. So the first thing I'm going to do is count how many ways are there to pick 3 different kinds. My hand has 3 different kinds in it, right? My example has an 8, a 9, and a queen. Okay? So there are 13 choose 3 ways to do that. So in my example, 8, 9, and queen. I think this is a really, these poker problems are not easy. They take a lot of practice. I think one thing that makes it easier is if you do exactly what I'm doing, like make up an example of a hand that looks like that, and then as you're counting the different steps to putting it together, you put, okay, after that step, what does your hand look like? Okay. So now the next thing I need to figure out of my 8, 9, queen, is which one of those is going to be the triple. Which one of those is going to be the 3 of a kind? Which of those 3 kinds is tripled? Is it the 8, the 9, or the queen? Well, I don't know, but I know that there are 3 choose 1 ways to make that choice. Okay? So after I've figured that out, now my hand looks like this. Uh-oh. I don't know what happened there. Oh, yes, I do. Right? Okay. Now I'm going to pick the suits for the triple. How many ways are there to do that? For just the triple. So in my example, it was hearts, diamonds, clubs. It could have been hearts, diamonds, spades. It could have been hearts, clubs, spades. Could have been diamonds, clubs, spades. That you can do as a combination, right? Because you need to pick 3 different ones. And it doesn't matter what order you pick them. So that's going to be a 4 choose 3.
What do they have to do with it?
Because there's only, for example, 1 8 of hearts. Right? Okay. So you pick which 3 suits are going to go on your triple card. Now when we get to these 2 cards, the suits can be repeated. Okay. So now we're going to pick the suits for the other 2 cards, and those can be repeated. Those can be repeated because they're different kinds. Oh, I forgot to fill in. So after step 3, my hand looks like this. Okay, but I don't know what suits the junk cards are yet. Well, you have 4 choices for what suit this is, and you have 4 choices for what suit that is, right? So 4 to the second. All right. Okay, so now I'm definitely going to need some help putting that all together. The number of outcomes in that event is 13 choose 3 times 3 choose 1 times 4 choose 3 times 4 to the second and what does that come out to? It's not going to be a huge number. $286 times 3 times 4 times 16. Somewhere around 4,000 or 5,000. Is that right? I could be off. No, maybe it's like 40,000, 50,000. 54,912. That actually sounds familiar. All right, 54, almost 55,000 different ways to get 3 of a kind. And so if we're talking probability, that is going to be somewhere around point what? .029? 0.021. So it's the third worst hand that's worth something in poker, and you only have a little bit more than a 2% chance of getting it. On the first draw, yeah. Yeah, you play a whole bunch of times. Eventually you'll get it. Oh, yeah. Draw poker is a lot more complicated. Okay. Number 5 is actually a lot easier than, well, definitely easier than 3 or 4. So I'm going to leave that up there. We'll take a little break. And then let's see what's coming up next. Oh, okay. Some stuff that you're kind of already familiar with. All right. Okay, so probability of winning a lottery by selecting the correct 6 numbers. So at least the really big lotteries like Powerball, Mega Millions, they're a little bit more complicated than that. This one's really, really simple. Yes. All right. So, yeah, how many ways are there to pick the numbers? How many different lottery tickets are there with 6 numbers on them? 59, choose 6, right? What is it? Okay. All right, so the event of picking the correct 6 numbers, and they have different prizes, right? There are runner-up prizes, like you win something if you match 5 of the numbers, for example. And so there may be problems like that. So again, I'm going to do this in the most general way I can. When you're doing a lottery problem, you're interested in how many of the numbers are right and how many of the numbers are wrong. Okay. So there are 6 correct numbers, and in this case I want to pick all 6 of them. And there are 53 numbers that are losers. You know what I have to remember? Oh, I wish I had remembered this for today. This would have been fun. I think I told you this story once before. So remember when the Powerball jackpot was over $1 billion a few months ago? So I broke down and bought 10 tickets. I don't usually play the lottery, but I decided, why not? I matched no numbers on any of my tickets. No numbers on any of my tickets. And I figured out what the probability of that was. And it was kind of funny. I'll try to bring... we might have time to do it today. Then I have to remember how the Powerball rules work. Okay. Anyway, there are 53 wrong numbers, and if I matched all 6 numbers, that means I didn't pick any of those. Well, 6 choose 6 comes out to 1, and 53 choose 0 comes out to 1, so that's not too surprising. There's exactly 1 good ticket if we're trying to win the jackpot. So in this particular lottery, the probability of winning the jackpot is 1 out of 45 million something. And that will leave as a fraction because as a decimal it would be 0.00000 something something. All right. Good? All right. So a couple more rules that come in handy. I think we've used, well, we have used one of these by accident. Problem 1.5. This one here. All right. So if E is an event, the probability of the event E complement is you just find the probability of E and subtract it from 1. All right. So the idea is either the event happens or it doesn't happen. It can't do both, all right? And it has to do one or the other, all right? So the probability of E and the probability of E complement have to add up to 1, as in 100%. And so where it's really useful is in this form, okay? So you already, like I said, we already used that once. We used it in the example number 1.5. That I did by accident. See, everything has a way of working out. I have a feeling I have one more of those on the next slide. And then, you've seen something like this before. If E1 and E2 are events, the probability of their union, which is the probability that one or the other of those things happens, You can find the probability of each event, add them together, but then there's a possibility that the events overlap, have some of the same outcomes, and you don't want to count those outcomes twice, and so you have to take out the intersection. You have already seen the counting version of that formula. We did it back in chapter 2, I think it was. Okay? All right, so what do we got? What is the probability of the... Okay. Yeah, you've seen something really, really similar to this now. All right. You should be able to do this. So let's leave that one out there. Actually, you know what I'm going to do? I'm feeling adventurous. Let's put both of these out there. We haven't done something exactly like number 2. We actually did. We did the counting version of this sometime in chapter 6, I think. Okay. I'd like to just leave those floating out there. Think about it for about, I don't know, 3-4 minutes. And I'm going to wander around. Okay, so let's talk about number 1. Number 1 really is exactly like the one we did earlier. Okay, except I might just write it a tiny little bit differently. So the probability of at least one heart, there's those words at least one again. All right. Using the complement rule, I'm going to say that that's equal to 1 minus the probability of no hearts. So the probability of no hearts, well, there are 52 choose 5 different hands. And so when I try to sort out the ones that are that have no hearts, first I'm going to pick my hearts and then I'm going to pick my other cards. How many hearts are there? 13. And I'm choosing none. 39 other cards. I need all 5 of my other cards, all 5 of my cards to come out of that other stack. Okay? What does 39 choose 5 come out to? 575. That's interesting. All right. Okay, so that fraction must be somewhere in the ballpark of 0.22. 1 minus 0.22, so about a 78% chance that your hand will have at least one heart in it. Okay? All right. This problem number 2, hopefully it kind of rang a vague bell, something we did in, I think it was chapter 6. So when you're trying to count how many numbers less than 500 are divisible by 6, I remember the last time we did this, it was how many numbers less than 1,000 are divisible by 7, and we also used 11, and we did both, and we did one or the other. We did a whole bunch of stuff. Okay, so the probability that your number is divisible by 6 or 9, this is using the second rule that you saw over here. Okay. So I remember this was either called the addition rule in Chapter 7, or I think it was called the addition rule, and it was also called the principle of inclusion-exclusion. It has the same name and probability. I don't know why it's not on there. But anyway, that's what you have to use for this one. So you have to find the probability the number is divisible by 6, the probability it's divisible by 9, and then subtract the probability it's divisible by both. Oh, I just thought of one thing that makes this a little bit trickier than the last one of these we did. Okay. So first of all, the denominator is easy. How many numbers are there to pick from? 500, right? So that's going to be your denominator. Okay, so now, numbers that are divisible by 6 would be 6, 12, 18, 24, 30, all the way up to whatever the last one is before 500. I don't know off the top of my head, and it doesn't really matter because that number is, how many of those there are is just do 500 divided by 6, which is definitely not an integer. All right, 500 is not divisible by 6, but you floor it. Remember? We did that with the problem with the 1,000 and the 7 and the 11. I think that comes out to 83. And then you do the same thing with the 9. Okay. Now here's where it gets tricky. Numbers that are divisible by 6 and by 9, a simpler way to say that is that they're divisible by, anybody know? 18. That's right. The last time we did this problem, it was 7 and 11. If a number is divisible by 7 and 11, it is divisible by 77. All right? Well, this time it doesn't work that way, because, and I guess it would have been helpful if we had done the number theory chapter for this. But if a number is divisible by 6 and by 9, it is divisible by 18, which is the least common multiple of 6 and 9. So you have to take out the ones that are divisible by 18. (18) is the least common multiple of 6 and 9. Okay. So I know this one is 83, and I know this one is 55. And then what's the other one? (27). 83 and 55 is 138 minus 27 is 111. So probability that your number is divisible by 7 or 11. I'm stuck in the other problem. 6 or 9 is about 22%. All right. Good? Okay. So before we get to the Monty Hall problem, I decided I want to do this Powerball thing first because it's kind of more related to what we're talking about, and because it's fun. All right. So Powerball, in case you didn't know, I had to look it up because they changed the rules recently. All right. They added more numbers, and the reason they added more numbers is they wanted more people to play. All right. And adding more numbers makes it harder to win, and it makes those jackpots build up a lot more All right, like over $1 billion. And when the jackpot's over $1 billion, you get tons and tons and tons of people playing. Okay. So the way the Powerball works now is that there are 69 white balls, numbered 1 through 69. You have to pick 5 of those. And then there are 26 red balls, numbered 1 through 26, and you have to pick 1 of those. And if you match all 6 of those, you win the big jackpot, whatever it is. Okay? So I thought that I could actually kill 2 birds with 1 stone here, because I was telling you the other day that you can do these permutation and combination things on Maple. And since I don't have a calculator, it's like a perfect storm of excuses to show you Maple for this. Okay, so I think the way this works is, this looks a little different than the last time I had it open. Where is my, oh, okay. I guess I can just do it, right? So in order to use permutations and combinations, I think you have to load the combinatorics package. Let me make the font bigger here. That's the combinatorics package. Okay. It's messing me up. It doesn't have the little caret thing for input anymore. Oh, okay. Yeah, I need that. Because what I just typed didn't do anything without that. There we go. Okay. So now I think the command for, okay. So let's talk first about how many different possible Powerball tickets are there. All right. Well, there are 69 choose 5 ways to pick the white numbers. And then with any set of white numbers, you can have any red number. So there are 26 choose 1 ways to get the red number. So the total possible number of tickets, I think this is how you do it. Why did it go back to 12? Am I going to have to do this every time? Okay. Let's try this. So I think it's NUMB, COMB, 69, 5. Okay. So 11,238,513 different selections of white numbers. White numbers. We still have to multiply that by the... Man, that is annoying. And I'm guessing this doesn't work. Okay. Does this still work? Okay. Yeah, what this does, in case you didn't know, this is like the ANS on the calculator. It just refers back to the last output that came out of Maple. There might be a different way. I'm working off Maple 5. Maple 5 is when I learned Maple, so I do a lot of things in a funny sort of way. All right, so 292 million. And some odd different possible tickets. Okay? So what happened to me is that I bought 10 tickets and matched absolutely no numbers on any of my tickets. All right? Now, there are other ways to lose Powerball than by not matching any of the numbers. If you only match one white number, that's not worth anything either. And I didn't even do that well. All right? I matched absolutely none of the numbers. And so what I want to count now is how many different tickets are just complete and total losers. All right? None of the white numbers are correct, and the red number is not correct either. All right? So next thing I'm counting is the number of completely wrong tickets, we'll call them. Oh, by the way, so this is your probability of winning the big jackpot, 1 out of that number. All right. And you have to be the only person who plays that number, which is a whole other thing. Okay, so if your ticket is a complete loser, that means that you picked all 5 of your white numbers out of the 64 that didn't win, and you picked your red number out of the 25 that didn't win. And that number comes out to, there must be a way to set that so that the output also. Okay. So this many tickets are complete losers, almost 191 million. So the probability that your ticket is a complete loser is last answer divided by second to last answer. I think that works. And if we change that into a decimal, 0.65 something something. So there's about a 1 in 3 chance that your ticket will have at least one good number on it. Okay. All right. So now I need to get a little bit ahead of myself for this next part. All right. I bought 10 tickets and they were all complete losers. All right. So the way that works, and we're going to get into this in either the next section or the section after. So if you bought more than 1 ticket, those are called independent events. All right. The numbers on the second ticket have nothing to do with the numbers on the first ticket. You're not trying to make them all different. You're not trying to do anything. The machine does not remember what were the last numbers that it picked. And by the way, I have to tell you, it wasn't this last time that the jackpot got huge. It was some other time. I was listening to some news show, and I actually heard somebody say that the red number that had been picked the most often was 36. All right. Must not have been Powerball then, if it was a 36. It must have been, it was probably Mega Millions or something. I don't know. And so the person went on to say, therefore, if you pick 36 for your red number, you have the best odds of winning. No. No. Just because that's the number that was picked the most often doesn't mean that the machines that pick the numbers are going to remember that. That's not the way it works. All right. Okay. So, tickets are all independent of each other. The machine doesn't remember what you picked before. So, when you want to find the probability that a bunch of events all happen, if those events are independent, I'm giving you a sneak preview here. I'll just tell you the rule for if there are 2 of them. The probability that events E1 and E2 both happen is equal to, you just multiply those probabilities together. If, okay, there's a very big if on that. We'll talk about this more later. If the events E1 and E2 are independent. And by the way, independent doesn't mean separate. It doesn't mean mutually exclusive. It just means sort of unrelated. Okay? And so, that means that if you buy 10 tickets, the probability that they are all complete losers is this number times itself 10 times. This number to the 10th power. And when you raise that number to the 10th power, that's not going to work. The probability of getting 10 tickets that are all complete losers is that much. But it happened to me. I feel like I should win a prize for that. All right. So that's my Powerball story. I guess we have time to talk about Monty Hall. Might as well. Okay. So I thought I'd kill a bunch of birds with one stone, show you some maple, tell my Powerball story, do another example. All right. Okay, Monty Hall. This is fun stuff here. So I'm guessing some of you are familiar with this problem. Okay. Which takes a little bit of the fun out of it, but that's okay. All right. So I think Let's Make a Deal still on TV, isn't it? I don't know that they play exactly the same way as they did back in. So Monty Hall is the name of the guy that used to host Let's Make a Deal. And now it's hosted by what, Wayne Brady or something? Isn't that right? Okay, that's the show where people go on and wear weird costumes and play games and okay. And one of the defining, charms of the show is that they give you all these different options. Do you want what's in the box or do you want what's behind the door? And sometimes one of those things is something you don't want, right? Like a year's supply of Spam or something like that, right? So the Monty Hall problem is this. So there are 3 doors, right? And you pick a door. You say, I want what's behind door number 1, or I want what's behind door number 3. Okay? So you pick one of those doors. Let's say door number 1, right? You might as well pick door number 1 because it's random. And the classic way to do this problem is that one of those doors has a new car behind it, and the other 2 doors have goats, all right, which is one of the dud prizes that I don't know. I've always wondered if they actually gave the person the goat. All right. Okay. So let's say, so everybody got it? One of these has a car behind it. The other 2 have goats. So let's say I pick door number 1. I say I want what's behind door number 1. Well, at least one of these other doors is going to have a goat behind it. So what Monty Hall is going to do is he's going to open the door, or a door, that has a goat behind it. All right? So let's say that there's a goat behind door number 3. He's going to open door number 3 and show me there's a goat there. And then he's going to ask me, do I want to stay with door number 1 or do I want to switch to door number 2? And the question is, what should I do? What should I do? Should I stay with door number 1 or should I switch? Okay. Now it sounds like most of you have, either heard the problem before or you're really, 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 really good. All right. Because most people, the first time they hear this, they say, it doesn't matter. It doesn't matter because, okay, I know I'm not going to pick this. This is sort of out of the equation. And so I've got a 50-50 shot. The car is either here or it's here. Okay? But it turns out, as some of you might know, that the best thing to do is actually to switch. And if you switch every single time, you will win on average 2 out of every 3 times. All right? And let me tell you, the first time I heard that, like everybody else, my first guess was it's 50-50. All right? And it took me a really long time to be convinced that it wasn't. A really, really, really long time. And it was one of these things where I would talk myself into it for a little while. Okay, I understand why you should switch. And then the following week, I'd be back on, no, I don't understand. I think it's 50-50. Until I heard an explanation that made sense to me. And then from that point on, I was totally convinced, never went back. And so, so my favorite way to explain it is like this. So first of all, let's say that you always pick door number 1. You might as well, right? Always start by picking door number 1. Now there are 3 possibilities. Possibility number 1 is the car is here. Possibility number 2 is the car is behind door number 2. Possibility number 3 is that the car is behind door number 3, right? Okay. So let's say that I'm always going to pick door number 1 and I'm always going to switch. Okay? Because I think that's the best way to do it. Well, if the car is behind door number 1, I'm going to lose, right? Because I pick door number 1, he opens one of these, it doesn't matter which one, but if I switch, I'm going to lose. So if the car is behind door number 1, you're going to lose. If the car is behind door number 2, and I pick door number 1, well then he's going to open door number 3, right? And show me there's a goat there. So if I switch to door number 2, I'm going to win. And if the car is behind door number 3, I'm also going to win, because then he's going to open door number 2 and show me there's a goat there. And so I'm going to switch to door number 3, and I'm going to win. So you should switch, and your chances of winning are 2 out of 3. Fun story. I haven't subscribed to a newspaper in a while, but the last time I did, on Sundays, there's this insert called, what is it called? Parade. That's what it's called. And it's this little thing, and it's got, you know, dumb news about celebrities in it, and it's got some puzzles in it. And one of the other things it has in it is a column called Ask Marilyn, written by a woman named Marilyn Vos Savant. I think that's a pen name. And Marilyn Vos Savant bills herself as the person with the world's highest IQ. And so people write in and ask her questions. And years and years and years ago, somebody wrote to her and asked her this question. And her answer was, you should switch. She has the world's highest IQ. Of course she said that. She got hate mail, including from a few PhD mathematicians. That's how counterintuitive this answer is. All right? So it's a really fun problem, and it's got some really fun stories behind it. But yes, you should switch. That's definitely the thing to do. And you'll win 2 out of every 3 times. All right. And so you might do a coding thing with that, maybe, possibly. Okay. All right. Well, that's all I have. So we're done 7.1. 7.1 is not on the exam next week. I will put homework up there. That is not on my, that's, okay, the higher priority things are grade your homework for Chapter 5 and put up the practice test. So I'll put up the practice test today. I think I'll have time to do that. And I'll return your homework to you by Tuesday. Okay?